The last segment in this particular soft chalk is going to be about energy and power. And we're not going to get into the weeds on this. Again, my point here with all of this is just to begin to orient you and get you used to some ideas, okay? So in circuits, if you've got an EMF, all right, whatever kind it is, you can, if you've got more than one EMF, you could put them in different configurations, okay? So you might, for example, put them over here like this, which is to say they're in parallel. Or you might stack them like this, which is to say you're going to put them in series, okay? Now, if we think about this like a pump, think about the battery as a pump for just a second. You need to realize that a pump is limited in how high it can push water up over it, okay? The higher the pump pushes the water, okay, the more force the weight of the water pushes back. And so at some point, the weight of the water column itself will be so great that the pump can't do it. And the pressure, the hydrostatic pressure from the water up above will match the hydrostatic pressure provided by the pump. And then your pump's in big trouble. Okay, you can't get any higher. So that, I don't know, maybe that's 30 feet or something like that. I don't know what it would be. Okay. Now, in this parallel situation, if we had two pumps, okay, each one of those pumps can only push the water up 30 feet over its head. All right. However, we could push twice as much water because we've got the two pumps. All right. So if we had a situation where we needed lots and lots of water, we would want to use two pumps. All right. So with our EMFs, if we needed a lot of current, then we might put our batteries side by side like this so they can put out a lot of current when combined together. All right. But if our pump can only push water up 30 feet in the air, what if we had to get to 50 feet? Okay, what we would do is we would use one pump on top of the other. Okay, so one pump takes it up 30 feet, and then the next pump would take it up however far we needed to. Okay, and so we could theoretically then get that up to 60 feet. Okay, and so this kind of configuration is for stacking EMFs going to increase our voltage. Okay, so in this case we're going to get twice as much current. Okay, but the same voltage. Okay, under ideal circumstances. Okay, there's some caveats, things we'll get into later. All right, and under ideal circumstances, in this time we'll get twice the voltage. Okay, but we have the same limit on current. Okay, so we're not going to get extra current through our batteries this way. Okay, however much current one battery can supply, that's kind of what we're going to be stuck with. All right, so now let's take this idea and let's break it down a little bit more. Okay, and we'll go back to our artificial stream here. And so if we want to think about the change in energy that our pump provides, here's our delta E, okay, that's a height change energy. So it's going to be the mass times gravity times the height change, mg delta H. Now we did that a lot back in the fall, so hopefully that is kind of familiar to you, okay? Now power is the time rate of change. So we could think of that kind of like how quickly we can add energy, all right? We add it really fast or we add it more slowly. And so it's a time rate of change, so it's a ddt onto the energy, okay? Now, for just a regular chunk of mass, okay, then this is going to be the mass times gravity times a dH dt, all right? So if I'm pulling up an object, then how fast can I pull that object up? All right, that becomes my power level right there. So I would say mgv, okay? However, we could look at it another way, and we could say it could be a dm dt G delta H, okay? Depending on how we need to look at it. And so we can also think of it as a flow rate, all right? So if you're going to be going 30 feet in the air, okay, how much, the power then depends on how much water you're moving, okay? How quickly are you moving the water, all right? So we've got different perspectives that are useful at different times. With electrical stuff, we have a similar situation, okay? So there's our two configurations. And for electrical stuff, the change in energy depends on the charge and the change in voltage, okay? So is it a 9-volt battery? Is it a 1.5-volt battery? What is all that kind of thing? What does that mean? Okay, and so then in terms of the power, all right, we can have a dV/dt or a ddt on that here. There's our ddt, okay? And in most of our configurations, the voltage isn't going to change, okay? We're going to leave that alone. And we're going to worry about this guy right here, dq/dt, all right? And so the dq/dt, that is our current. That's how much charge is coming out of our EMF, okay? And so then the power, how much energy we're using, depends on how much current we draw or we're using, and the change in voltage. All right. So what does all that kind of mean? Well, what it means for what voltage is that voltage is kind of like this term right here. Okay. So in order to get energy out of G delta H, we have to multiply by M. In order to get energy out of voltage, we got to multiply by a charge like this, okay? So when we say it's a 9-volt battery or a 1.5-volt battery, that's really kind of like a shortcut way of enabling us to get to how much energy that particular battery could put into the system, all right? And so we've got, when we have a voltage increase and then voltage drops around a circuit, we're adding energy, and then energy's bleeding out as we move on down the line, okay? So we gain height, we lose height. We gain voltage, which we could connect to energy, and then we lose voltage, which is connected to energy, okay? All the way around just like that, okay? Now we'll get into the weeds on some of these things later, but we're planting some seeds right now, and anyway, there we go. Okay, so I got just a few questions to follow up on this video here.